Welcome! In this session, we're diving into problem number 1526, titled Minimum Number of Increments on Subarrays to Form a Target Array. Together, we'll explore the problem, understand the challenges, and break down the approaches to solve it. Let's get started. In this problem, we're tasked with transforming an array called ARR into a given target array using the minimum number of operations. Initially, ARR is an array of zeros with the same size as the target array. An operation allows us to select any contiguous subarray of RR and increment all the elements in that subarray by 1. The goal is to determine the minimum number of such operations required to make ARR identical to the target array. The input consists of an integer array called target with a size between 1 and 10 to the power of 5, and each element in target lies between 1 and 10 to the power of 5. The output is a single integer representing the minimum number of operations needed. Let's explore some examples to clarify how this transformation works. In the first example, the target array is 1, 2, 3, 2, 1. To achieve this, we can start by incrementing the entire array once, which sets all elements to 1. Next, we increment the subarray from index 1 to 3, raising the middle section to 2. Finally, we increment only the element at index 2, bringing it up to 3. After these 3 steps, ARR matches the target, so the answer is 3 operations. In the second example, where the target is 3, 3, 3, 3, we can increment the entire array 3 times to reach the desired value of 3 for all elements. This also requires exactly 3 operations. Now, consider the third example. The target array is 3, 1, 1, 2. First, we increment the entire array once, setting all elements to 1. Then, to match the target at index 0, we increment the first element twice more, making it 3. Finally, we increment the last element once to turn it into 2. Altogether, this transformation requires 4 operations. This example highlights how the number of operations depends on the differences between values in the target array and how we can use subarray increments strategically to minimize the total steps. Looking at the constraints and edge cases helps us understand the problem further. For instance, in a single element target array, the result is simply the value of that element since no subarray selection is needed. For a uniform array, where all elements are the same, the result is equal to that repeated value. In a strictly increasing array, the output equals the last element, as each new value requires an additional operation. These patterns give us insight into the relationship between the target array's structure and the number of operations needed. Finally, arrays with sparse peaks or large jumps, like 5, 1, 1, 5, demand careful handling. Here, the output is 7 because of the need to address both the initial peak and the later rise separately. A key observation is that the number of operations corresponds to the sum of positive differences between consecutive elements in the target array, plus the value of the first element. This approach ensures that we account for all required increments efficiently, leveraging the differences in the target array to minimize redundant operations. To solve this problem, we first considered a brute force approach. The intuition here is straightforward: start with an array initialized to zeros and increment subarrays repeatedly until it matches the target array. For each element in target, we increment the corresponding subarray from the current value in ARR to the desired value in target. However, this approach has a few key drawbacks. Since each operation modifies a subarray, we end up performing redundant increments, which significantly increases the number of operations. This inefficiency becomes especially pronounced with larger arrays, leading to a time complexity of n squared. To address this, we recognized an important observation: the number of increments needed for a specific element in the target array depends only on the difference between its value and the value of the previous element. This insight forms the basis of an optimized approach, where we avoid simulating the entire process and instead directly calculate the necessary increments. By focusing only on differences between consecutive elements, we can drastically reduce the computational overhead. Next, let's break down the optimized approach into clear, actionable steps. First, we compute the total increments required. To do this, we start by adding the first element of the target array, as it determines the number of operations needed to initialize the first value. Then, for each subsequent element, we add the difference between the current element and the previous one, but only if this difference is positive. This ensures we account only for the additional increments required when moving from one value to the next. Once we've calculated these values, we return their sum as the result. This approach is highly efficient, with a time complexity of O(n), since we only iterate through the target array once. While we explored alternative methods, such as using a stack or dynamic programming, these added unnecessary complexity without providing meaningful performance improvements. By sticking to this straightforward logic, we achieve optimal results while keeping the solution clean and efficient. Ultimately, we chose the optimized approach because of its simplicity and efficiency. By leveraging the differences between consecutive elements in the target array, we eliminate redundant computations and achieve a linear time complexity. This makes the solution scalable, even for very large arrays, such as those with up to 100,000 elements. There are, of course, trade-offs to consider. While the brute force approach is easier to conceptualize and implement, it is computationally expensive and unsuitable for larger datasets. The optimized approach, on the other hand, requires a deeper understanding of the problem structure but pays off with significantly better performance. The decision to use this method aligns with our goal of minimizing both time and space complexity. With a final complexity of O(n) in time and O(1) in space, this strategy ensures we solve the problem efficiently without resorting to unnecessary simulations or complex data structures. To solve this problem, we are given a target array of integers, and we need to transform an initial array ARR, filled with zeros, into the target array. The transformation is done by incrementing subarrays of ARR. Our goal is to determine the minimum number of increment operations required to achieve this transformation. To start, we initialize ARR as an array of zeros, matching the size of target. We also set up an operations counter to track the number of increment operations performed. Then, we traverse the target array. At each index, we compare the current value of ARR at that index with the corresponding value in target to decide whether an increment operation is needed. Now, during the traversal, if the value at ARR, I, is less than target, I, it means we need to perform an increment operation. The difference between target, I, and ARR, I, tells us how much we need to increase the value. We increment the operations counter once for this subarray increment, as the entire subarray starting from index I is conceptually increment. However, since we are only interested in the final state of ARR, we can simply update ARR, I, to match target, I, without explicitly modifying the entire subarray. If ARR, I, is already greater than or equal to target, I, no operation is needed at that index. After completing the traversal, the value stored in the operations counter will represent the minimum number of operations required. The core insight here is that each increment operation starts at a specific index in ARR, and we only need to count how many such operations are necessary. Instead of explicitly simulating the increment process for each subarray, we can simplify the problem by focusing on how many times a new increment needs to start. By analyzing the target array, we realize that the number of operations is determined by the differences between consecutive elements. To optimize the approach, we initialize operations to the value of the first element in target, as it always takes that many operations to reach its value. For subsequent indices, if the current value in target is greater than the previous value, the difference between the two is added to operations. This eliminates the need to explicitly maintain the ARR array. From a data structure's perspective, the solution is highly efficient. The target array is the only input we need to process, and the operations counter is a simple integer variable that tracks the total number of required operations. This means no additional data structures are needed, as we avoid explicitly simulating the ARR array. For the complexity analysis, the time complexity is O(n), where n is the size of the target array, because we perform a single pass over the array. The space complexity is O(1), as we use only a constant amount of extra space. This makes the algorithm both time and space efficient. Let's work through an example to see the algorithm in action. Suppose the input is target equals 3, 4, 5, 1, 1. First, we initialize operations to target 0, which is 3, because we need 3 operations to reach the first value. Then, we compare consecutive elements in target. The difference between target 1 and target 0 is 1, so we add 1 to operations, making the total 4. Similarly, the difference between target 2 and target 1 is also 1, so we add another 1, making the total 5. For target 3 and target 2, the difference is negative, so no addition is made. Finally, the difference between target 4 and target 3 is 0, so again, no addition is made. The final value of operations is 5, which is the minimum number of operations required. Let's consider some edge cases. If the target array contains only zeros, no operations are needed since the initial ARR is already identical to target. For a single element array, the number of operations is simply the value of that element, as only one increment operation is needed. In the case of a strictly increasing sequence, each element contributes to the total number of operations based on the difference from the previous value. For mixed sequences with increases and decreases, the algorithm correctly handles fluctuations by only adding positive differences to the operation count. These examples demonstrate the robustness of the approach in handling various scenarios. The solution to LeetCode problem number 1526, minimum number of increments on subarrays to form a target array, involves calculating the minimum number of operations required to transform an array of zeros into the target array using subarray increments. Explanation of the code. 1. Initialization. The first operation count is initialized to the first element of the target array, target 0. This is because we need at least target 0 operations to make the first element of the 0 array equal to it. 2. Iterating through the array. The loop starts from the second element, I equals 1, and goes through the entire array. For each element, if target I is greater than the previous element, target I1, the difference, target I1, is added to the operation count. This accounts for the additional increments needed to raise the subarray up to the new value. If target I is less than or equal to target I1, no new operations are needed because the array already has sufficient increments to match or exceed the current value. 3. Return the operation count. After the loop completes, the total operation count is returned. Key insights. The problem can be reduced to calculating the cumulative increase in the target array values as we move from left to right. This approach is efficient with a time complexity of O(n), where n is the length of the target array, because it involves a single pass through the array. The space complexity is O(1), since no additional data structures are used. This solution is optimal and handles all edge cases, including arrays with a single element and arrays with non-increasing sequences. This is the Java implementation of LeetCode problem number 1526, minimum number of increments on subarrays to form a target array. The logic mirrors the Python solution provided above. The method iterates through the array and calculates the number of operations based on the difference between consecutive elements, adding the difference only when the current element is greater than the previous one. Key differences include the use of Java-specific syntax such as type declarations for the array and method signature. Here, we start with a simple example where the target array is 3, 1, 2, 4. To begin, we initialize the total number of operations as the first element of the array, which is 3. This represents the operations needed to increment the first subarray to match the target's first value. Next, we iterate through the rest of the array. At index 1, the value is 1, which is less than or equal to the previous value, so no additional operations are needed. Operations remain at 3. At index 2, we see the value 2 is greater than the previous value 1. The difference, which is 1, is added to the operations, bringing the total to 4. At index 3, the value is 4, again greater than the previous value 2. The difference, for minus 2, equals 2, so we add that to the total, resulting in 6 operations. The visual representation shows how we increment the entire array to 3, 3, 3, 3, using 3 operations, and then make targeted adjustments to match the target array, requiring 3 more operations, for a final total of 6. Now let's look at another example where the target array is 5, 4, 3, 2, 1, which is strictly decreasing. We initialize the operations with the first element, 5. This accounts for incrementing the entire array to 5, 5, 5, 5, 5. As we iterate through the array, we observe that at index 1, the value 4 is less than or equal to the previous value 5, meaning no additional increments are needed. operations remain at 5. The same logic applies to indices 2, 3, and 4, as each subsequent value is less than or equal to the previous one. No further operations are required, and the total remains 5. The visual representation highlights that while we initially increase the array to 5, 5, 5, 5, 5, the rest of the target array can be achieved without any additional work, making the final result 5. Now let's examine a more complex case with the target array 1, 3, 2, 5, 4. We start by initializing the operations with the first element, which is 1. This handles the first subarray increment. At index 1, the value 3 is greater than the previous value 1. The difference, 3 minus 1, is 2, so we add that to operations, giving a new total of 3. At index 2, the value 2 is less than or equal to the previous value 3, so no additional increments are needed, and the total remains 3. Then, at index 3, the value 5 is greater than the previous value 2. The difference, 5 minus 2, equals 3, which is added to the operations, bringing the total to 6. Finally, at index 4, the value 4 is less than or equal to the previous value 5, meaning no further increments are needed. The visual representation shows the intermediate steps, first, incrementing the array to 1, 3, 3, 3, 3, using 3 operations, and then adjusting the third index by 3 to achieve the target array's final form. The total operations required are 6. For this example, the final output is 6. This confirms that even for a more complex case, the algorithm efficiently calculates the minimum number of increments needed to shape the target array. By iterating through the array and only adding the differences where values increase, we ensure that we use the fewest operations possible. We begin by analyzing the time complexity of the solution. The algorithm iterates through the target array exactly once. It starts with an initialization step where the first element of the array is assigned to the operations variable. This step takes constant time, or O1. Then, we have a for loop that processes the rest of the array, from index 1 to the end. During each iteration, the algorithm checks whether the current element is greater than the previous one. This condition is evaluated in O1. If the condition is true, the difference between the current and previous elements is calculated and added to operations, which also takes O1. Since the loop executes one time for each of the N1 elements after the first, and each iteration involves only constant time operations, the overall time complexity of the solution is O(n). Now, let's look at the space complexity. The algorithm uses only a constant amount of extra space. Specifically, the operations variable, which keeps track of the total increments, and the loop index I are the only additional variables required. Both of these consume O1 space. Importantly, the input array target is not modified during the algorithm, and no additional data structures are created to store intermediate results. Therefore, the total space complexity is O1, as the algorithm's memory usage does not grow with the size of the input. Let's compare this optimized approach with a naive or brute force solution. A naive algorithm would try to increment elements one subarray at a time until the target array is formed. This process requires iterating over all possible subarrays and incrementing their values, which leads to a time complexity of O(n squared, in the best case and O(n cubed, in the worst case, depending on how the implementation handles overlapping subarrays. In contrast, the optimized algorithm leverages the observation that only the differences between consecutive elements matter. By focusing on the sum of positive differences and including the value of the first element, it avoids the need to repeatedly modify subarrays. This insight reduces the time complexity to O(n), which is a dramatic improvement over the naive approach. Next, we examine the best, worst, and average case scenarios for the algorithm. In the best case, all elements of the target array are the same. Here, the loop completes without adding any differences, and the time complexity remains O(n), because the loop still iterates through the array. In the worst case, the array is strictly increasing. Although the loop adds differences at every step, the work per iteration is still constant, so the time complexity remains O(n). On average, the loop still runs O(n), with positive differences being added for roughly half of the elements. To prove that the time complexity is indeed O(n), we note that the total work is the product of the number of iterations, which is proportional to the size of the array, and the constant amount of work done per iteration. This gives us O(n*(O1), resulting in O(n). Finally, let's break down the memory usage of the algorithm. The space required for variables like operations and the loop index I is constant, or O1. The input array target itself consumes O(n) space, but this is considered input space, not extra space, as it is provided as part of the problem. Importantly, the algorithm does not allocate any additional memory for data structures or intermediate computations. As a result, the total extra space used by the algorithm is O1. This efficient use of memory highlights the simplicity of the solution's design. Common mistakes can often trip up your solution, so it's important to recognize and address them early. First, failing to fully understand the constraints of the problem can lead to inefficient solutions. For instance, if the array size can go up to 10 to the power of 5, using a brute force approach with O(n²), complexity will almost certainly result in a timeout. Instead, analyze the constraints up front to gauge the feasibility of your approach. Another frequent issue is overcomplicating the logic. When trying to manipulate subarrays or calculate increments, it's easy to make your solution unnecessarily complex, which can introduce bugs and inefficiency. Aim to break the problem into smaller, manageable parts and focus on clarity. Lastly, incorrect subarray updates are a common pitfall, especially when the problem involves range-based operations. Miscalculating the start or end indices can derail your solution, so it's essential to carefully track these values and test against edge cases like single-element arrays or full-length updates. Another critical area to watch out for is ignoring edge cases. Examples include arrays that are empty, contain only one element, or have all elements being the same. Missing these scenarios can cause your solution to fail specific test cases. A good habit is to write out potential edge cases before coding and ensure your solution handles them effectively. Mismanaging time complexity is another common mistake. When working with large inputs, algorithms with nested loops or unoptimized operations can lead to time-limit-exceeded errors. To address this, explore optimized techniques such as greedy algorithms, prefix sums, or advanced data structures like segment trees. These approaches can significantly improve performance and ensure your solution scales well with larger constraints. Now, let's delve into some interview insights that can help you approach this problem more effectively. Recognizing patterns is key. This problem often benefits from techniques like prefix sums, difference arrays, or greedy strategies. Being able to identify these patterns quickly can save you valuable time during an interview. When discussing your solution, focus on presenting the optimal approach. If your initial solution is too slow, explain why and pivot to a more efficient method. Additionally, highlighting edge cases during the discussion demonstrates thoroughness and ensures your solution is robust. For example, mention scenarios like arrays with repeated values or the largest possible input size. If you're considering multiple approaches, take a moment to explain the trade-offs. For instance, you might compare a greedy solution that uses less computation time to a more memory-intensive approach, showing that you're thoughtfully weighing the pros and cons of each method. To deepen your understanding of this problem, exploring related problems can be highly beneficial. For instance, LeetCode 370, Range Addition, involves incrementing subarrays and introduces the concept of using a difference array, which is closely tied to this problem. LeetCode 1094, Carpooling, focuses on managing range-based operations, utilizing prefix sums to track passenger capacity. LeetCode 253, Meeting Rooms 2, is another relevant problem as it involves tracking overlapping intervals, which can help you refine your understanding of range updates. Finally, LeetCode 152, Maximum Product Subarray, emphasizes subarray manipulations and edge case handling, making it a valuable exercise for improving your problem-solving skills in array-based challenges. When tackling this problem, it's worth considering the various approaches and their trade-offs. A brute force solution is straightforward to implement, but it's highly inefficient for large input sizes, often resulting in O(n²) or worse. This method is only suitable when constraints are small. A greedy approach, on the other hand, is often optimal for problems that involve making sequential decisions. While it can save computation time, it may require additional logic to handle edge cases properly. The prefix sum or difference array technique offers an efficient O(n) solution, making it ideal for range update problems. However, it requires a solid understanding of pre-computations and careful implementation to avoid mistakes. For more advanced scenarios, segment trees are a powerful tool for dynamic range updates, but they come with a steep learning curve and involve complex implementation. Choosing the right approach depends on the constraints and requirements of the problem, so weigh these trade-offs carefully to arrive at the most effective solution. Thanks for sticking with us. To summarize, we explored the problem, analyzed approaches, and discussed key takeaways. We hope you found this walkthrough insightful. Don't forget to like, share, and subscribe for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!